So this talk is about Robosat. It's a generic ecosystem designed to perform quality evaluation and feature extraction based on imagery. It could be aerial or satellite even. And you've got the both GitHub. The point is it's a state-of-art SAMSEG. But it's also designed with an industrial design and conversion, so it's really usable in production. It's by design something really modular with several bricks, so things Lego, and you will have to perform a treatment chain with that. It's really close to OpenStreetMap and Mapbox ecosystem. It's on top of PyTorch, and is on a very permissive license. So if we look about a neural treatment, if we want to train in a supervised way, we need data labels, neural networks, loss function, and weights. So the first thing to help us with any kind of platform will be to help us on the data preparation, and Robosat help us with several kind of tools. The pink ones are several tools provided inside Robosat. And the whole aim is to help you to prepare your training data set. So it could help us, for example, to tile a raster, to download imagery from a remote server, to extract some data from OpenStreetMap, vector, and so on and so on. So the aim is to, at the end, is able to create a training data set quite easily and without too much pain in the process to really be able to focus on the main interesting part. So it's just a way to help you to do it quickly. So the core is really itself the neural network topology. As I said, it's state-of-art. It's based on the non-encoder-decoder network. Historically, it was UNet was the first to bring something usable. Here, the first encoder is based on ResNet 50. So you already convey all the ability to classify from a ResNet classifier. And on the bottom part, on the decoder, it's the symmetric part. It's also able to deal with multi-band imagery. So, for example, if you have imagery, we provide not only RGB, but for example, infrared or some other bands, you're able to play with. And you could also rasterize some vector data in additional and put them into your tensor. So for instance, if you have related data from your imagery, you could build a tensor with more than only the RGB imagery. The next point is the loss function. So classically, in imagery, we use a cross entropy. We provide some results, but some poor result because it doesn't use all the topological parts conveyed by the imagery. So in fact, there is new Bonnard losses who are able to help on the training part, and they are also provided inside Robosat. So you can use both surrogate on intersection over union and the Lovács losses. And the last point is the weights. So on the weight, you could obviously use some ResNet 50 model already pre-trained on ImageNet. It's an optional, so you're not obliged, but you can. You can resume your training, so at a point you could reuse your training for one train to another, and you could export on NX6 to use back on another with another platform model if you want. So I don't know if you were at the really beginning presentation of this morning, but it was about ONNX. If we look at one use case, if we took open data from Lyon, it's an imagery web services, and the related buildings footprint, we download the imagery, we rasterize the footprints to create image and label. We split the data set between train and train validation, and then we can launch the train itself, create the model, and then predict with the image some masks, and then we are able to compare if it's okay, yes or no. So if we look here on the result, we've got in pink what have been found by the model, what have been predicted. And in green, it's the opposite. It's when the label said that there was something, but the model didn't predict it. And in gray, it's the complementarity additional color. So when it's gray, both are gray. So you just have to look at the pink to say, okay, the model detects something in more, or you just have to look at the green to say, okay, the label says something more. And when it's gray, both are okay. So we achieve some kind of quite good result. And it's interesting because by design, the goal is to be able to show if there is a difference between two data sets. So it helps to see if there is a difference between the two, if it's our model was not well trained enough, or if really the data set itself is crappy. And obviously, if there is some missing label inside the data set, the model is able to detect them. But the point is not only to check our model between our imagery and the label. You could also use some other feature, rasterize them, and compare. And so, for instance, you could then, with a QOD value, detect where there is some issue on the whole grid, and then only choose to zoom in to see on a specific tile why even there is an issue on it. So it's a quick way to look what is different on your whole data set. What about the stack? About Robosat itself, there is a geospatial stack, a machine learning stack, and an image manipulation one. So all of them are based on Python API, but there is several combination of software able to, at the end, convey only a few lines of Python to achieve it. What is the timeline? It's really something new. The first release was in August from this year. It was the first one, and it was provided by 2 developers from Mapbox. In September, there was a new version, a new release, was focused on increase the performances. So right now, it's able to play well on multi-GPU and with a lower footprint on GPU memory. In the master of the GitHub, there is OpenStreetMap prod extraction, and the new losses implementation. And it's still on pull request, the ability to play with multi-bands and with additional tools, as I show you on this presentation. And on the Mapbox side, they play well with the community source integration. So the code review is a really good one, and they are really okay to pull request some new code. What next? Right now, the product performance needs some improvement. We can do on a single GPU something like 30 images per second. It's quite good, but it's not at all good enough if we want at scale to treat something like a whole country or the whole world. So the product performances have to be improved at scale. The resolution, now we deal with high resolution, but it will be really something more interesting to be able to play with low resolution imagery. And we have quite a way to achieve it. And the third will be the feature extraction, but it's implied to be able to post-treat our data. As right now, it's something quite good to detect if there is something different in two datasets, but not good enough without post-treatment to really be able to do something interesting with the post-treatment. So if we focus on the first performances issue, there is already on the new coming PyTorch version something could help to improve the performances is the JIT just-in-time compiler conveyed by PyTorch. There is also in the latest CUDA version the ability to reduce the precision of the digit we use inside the weights, so we could save the footprint in memory. And as we can export in non-NX, we can try with other environments if there is any performances gain. And also, ResNet is really efficient, but it's not the more lightweight model available. So we can do a lot by reducing the size of the model itself. On the resolution, we know we can improve again the topological and fusion process. As an input, there is also superpixel resolution, who can also help as an input for lower imagery input. And for feature extraction, Robosat right now provides some classical tool to help to play with, but it will be really interesting to explore more generic way, like GAN, for instance. As a takeaway, right now there is some IOL semantic segmentation platform available and usable. The data are also available, but the point is that the labels themselves are not that good. There is no really good open data set available with imagery from all over the world. It's really easy to find imagery. It's really easy to find geometrical information, but as a feature, not as a mask. So if you want a good semantic segmentation, the current bottleneck is to build an open data set available all over the world with really good data as mask and not as a feature. And as I said, the predicted speech performances should be still improved. So that's it, and thanks. And I show you just yes what we do. So that's the place where on the you can see that here there is something. Okay, so it was a demo size. So the question.
We have some time for question.
Yep.
Thank you for your talk. Just so developing this open data set seems the way to go, but it also seems to be a huge task. Do you have any recommendations for how to develop this data set? How should the community get organized for this?
With Robosat, we have the compare tool. The compare tool is able to compare an imagery and another rasterize data, and to, as an output, produce either an imagery of the difference or a metric. So we can, with this platform, produce distance metric between two data sets, and then use human to switch, to say, okay, yes or no, yes or no, yes or no. So we are already all the tool to make easy or easier a way to achieve an open data set creation, but at the moment we need humans to say yes, no, yes, no, yes, no. So
last question. So thank you, Olivier.
Thanks.